The transition from analyzing isolated business functions to mastering end-to-end supply chain engineering requires a complete shift in how we define operational architecture. A common misconception in management is the idea that understanding a single component, like a specific warehouse or a shipping lane, is sufficient to understand how the entire enterprise operates. Every system exists to achieve an overarching outcome that its individual components are incapable of achieving independently. The architecture is built specifically to convert initial inputs into final outputs in a strictly controlled and repeatable manner. This enables optimization at the level of the whole, rather than the local level. In a high-functioning system, local sub-optimization is intentionally avoided to protect the global result. To build a functional supply chain, engineers must move past the study of individual parts and focus on the structural links that bind them together. A system is a set of interrelated components working toward a common purpose, where behavior of the whole emerges from the interactions among parts. This principle of emergence is critical. It means the behavior of the entire structure dictates the final outcome, not the isolated parts themselves. We apply this definition to a tangible business model by mapping a standard macro supply chain. The flow begins with suppliers, moving sequentially through factories, warehouses, and transportation networks until it reaches the end customer. Within this macro system are microsystems. A single production floor, comprising machines, labor, and materials, functions as a system within the larger factory node. Regardless of the scale, the laws of emergence govern the final operational output of the network. For any system to function without collapsing, it requires a specific structural anatomy. Inputs, such as raw resources or demand signals, move through transformation processes to become final outputs. System boundaries define what is under direct operational control versus the external environmental forces that influence the flow from the outside. Survival and adjustment within those boundaries depend on a mechanism for self-regulation, the feedback loop. Performance signals must travel backward from the output to the input, allowing for real-time adjustment based on actual results. These signals dictate whether the system stabilizes its output or spirals out of control. Without high-speed feedback, a supply chain is blind to its environment and cannot regulate its own transformation processes. Because of interdependence, changing the speed or capacity of a single operational node impacts every subsequent node in the chain. The theory of constraints states that every system contains a bottleneck that sets the absolute maximum limit for total end-to-end output. Maximizing efficiency at a department that is not the bottleneck only creates excess inventory and systemic waste. Validating the integrated approach requires shifting focus from the individual department to the global flow. Systems dynamics principles teach us that structure drives behavior. The architecture dictates success, regardless of the effort level of individual teams. In these massive systems, cause and effect are rarely immediate. They are often delayed and nonlinear. This is why focusing on 100% efficiency in an isolated department is mathematically guaranteed to damage global performance. Applying systems thinking allows us to move from theory into practical operational engineering. Engineers use this framework to design supply networks, implement cross-functional planning, and diagnose the root causes of operational failure. Within this context, key performance indicators are the formalized feedback mechanisms that keep the system within its operating parameters. Modern globalization and digitalization have increased system complexity to a level that makes manual oversight impossible. The pursuit of hyper-efficiency, such as just-in-time models, creates tight coupling. While this maximizes speed, it also increases system fragility during environmental shocks. The mandate in modern engineering is shifting away from purely designing for isolated efficiency and toward designing for systemic resilience. We can distill these concepts into a practical diagnostic framework for analyzing any operation. There are 3 mandatory questions required to validate the health and design of any supply chain or process. First, identify the true end-to-end purpose of the network, ensuring it isn't being superseded by local departmental goals. Second, locate the structural bottleneck that is currently dictating the capacity of the entire system. Third, map how feedback data loops back to influence real-time management decisions. Applying these 3 questions marks the leap from merely managing tasks to architecting optimized end-to-end supply chains.